In this video, in the complex number theme, we're going to have a look at how a small amount of information about the solution of a polynomial equation will often enable us to find all of the solutions. So we'll start by considering the example. We've got f of x is equal to x cubed minus 6x squared plus 17x minus 18. We're asked to evaluate f of 2 and hence find all the roots, both real and complex, of the equation z cubed minus 6z squared plus 17z minus 18 equals 0. Now, we've got to start by finding the value of f of 2. Well, f of 2 is 2 cubed, take away 6 times 2 squared, add 17 times 2, take away 18. So that is 8 minus 24 plus 34, take away 18, and that comes down to 0. So that means that we've found our first root of the equation z cubed minus 6z squared plus 17z minus 18 equals 0. We know z equals 2 is a root of the equation. Now the factor theorem tells me that z minus 2 must therefore be a factor of z cubed minus 6z squared plus 17z minus 18. So let's see whether we can do the factorisation. So we're going to say that z cubed minus 6z squared plus 17z minus 18 is z minus 2 times something. Now, it should first of all be immediately clear that inside the square brackets we're going to need z squared because we've got to get a z cubed term out of our factorisation. And the only place we can get that from is by having z times z squared. Also, if we look at the constant term, when we do the expansion, we've got minus 18 as the constant term. So minus 18 must come from minus 2 times by plus 9. So we must have plus 9 at the end of the factorisation. Now the only thing we're not sure about is what goes in the middle of the factorisation, what the z term in the factorisation is. So a fairly neat way of finding out what this is to say, okay, I know I've got a z term in the middle, let's call it a times z. And then what we'll try and do is we'll work out what the value of a is. So considering the z squared terms, in z cubed minus 6z squared plus 17z minus 18, the z squared term is minus 6. So we've got minus 6 must equal the z squared term when we multiply out z minus 2 times by z squared plus az plus 9. Well, looking carefully, we can see that we're going to get a z squared term when we multiply the minus 2 by z squared, and that will give me minus 2z squared, but we're also going to get a z squared term when we multiply the z by the az, and that's going to give me az squared. So the factorisation is going to work. I need to have minus 6 equals minus 2 plus a. In other words, a must be minus 4. So we reckon the factorisation is z minus 2 times z squared minus 4z plus 9. But it would be worthwhile checking the final term. We'll check the z term. That's the only one we haven't checked is correct at the moment. So where do the z terms come from when we expand out the brackets? Well, we're going to get a z term from minus 2 times by minus 4z. So that gives me 8z. So I've got 8z coming from there. But I've also got z terms coming from the z times by the 9, which gives me 9z. So in terms of the right hand side, I've got 8 plus 9, which is 17 lots of z, which is exactly what I want because I've got 17z on the left hand side. So we now know the factorisation is correct. So If I want to solve z cubed minus 6z squared plus 17z minus 18 equals 0, I know that either z minus 2 equals 0 or z squared minus 4z plus 9 equals 0. So that tells me that either I've got z equals 2 or I've got z squared minus 4z plus 9 equals 0, and I can use any of my normal means of solving a quadratic equation to deduce that that gives me z equals 2 plus or minus root 5i. Now, notice that all of the coefficients of the original function, of the original polynomial, are real numbers. When that is the case, we say that f is a real polynomial. So a real polynomial is one that has all the coefficients of the powers being real numbers. And the second thing to notice at this stage is that the roots of f, or the roots of our equation, consist of a real number, that is 2, together with a complex root, 2 plus root 5i, and its complex conjugate, 2 minus root 5i. Now, there's a very important result, which says that if we have p is a polynomial with real coefficients, and if alpha plus I beta is a root of the equation p of x equals 0, then alpha minus I beta is also going to be a root of the equation p of x equals 0. In other words, if we have a real polynomial, then the complex roots appear in pairs, the complex root together with its complex conjugate. Now, to establish this important result, we need to set up a few properties about conjugates. The first one is simply the definition. If z is the complex number alpha plus I beta, then the complex conjugate of z is z bar, where z bar is alpha minus I beta. Notice that some people may use a star rather than a bar to denote complex conjugates. Throughout this video we're using z bar to denote the complex conjugate of z. The second result simply says that the complex conjugate of z plus w is the same thing as the complex conjugate of z plus the complex conjugate of w. And the proof of this is displayed on screen at the moment and simply goes through the process of saying, okay, let z equal alpha plus I beta and w equal gamma plus I delta. Then the complex conjugate of z plus w is the complex conjugate of alpha plus I beta plus gamma plus I delta. Now, to add those two complex numbers, we simply add the real bits and add the imaginary bits. So z plus w is the same thing as alpha plus gamma plus I times beta plus delta. So the complex conjugate of z plus w is the complex conjugate of alpha plus gamma plus I times beta plus delta, which gives me alpha plus gamma minus I times beta plus delta, or in other words, alpha minus I beta plus gamma minus I delta, which is the complex conjugate of z plus the complex conjugate of w. So we've now shown that the complex conjugate of z plus w is the same thing as the complex conjugate of z plus the complex conjugate of w. And this result can be easily extended to adding 3 or 4 or 5 or 6 or any number of complex numbers together. So the complex conjugate of a sum of complex numbers is the same thing as the sum of the complex conjugates of each of those numbers. The third property says that if we have two complex conjugates and we multiply them together, then the complex conjugate of Z times W is exactly the same thing as the complex conjugate of Z times by the complex conjugate of W. And again, this is a fairly simple algebraic proof. I shall leave you just to read through that one. And the final result about complex conjugates that we're going to need is one that says that if we have a complex number Z, then the complex conjugate of Z to the n is the same thing as the complex conjugate of Z raised to the power n. And this can be proved fairly easily using a proof by induction. And again, in order to, I'd suggest that you just pause the video for a couple of minutes and check that you can follow the proof by induction. It's a relatively straightforward one. So let's move now on to the proof of our main result. So we've got p of x is a polynomial with real coefficients. We've got alpha plus I beta is one root of the equation p of x equals 0, and we want to show that alpha minus I beta must also be a root of the equation. So let's suppose that p of x is an times x to the n plus an minus 1 x to the n minus 1 all the way down to a1 times x plus a0. We know that alpha plus I beta is a root, so if we denote alpha plus I beta by z, then we've got p of z equals 0. In other words, we've got an z to the n plus an minus 1 z to the n minus 1 all the way down to a1 z plus a0 equals 0. And if you like, you could regard 0 as being 0 plus 0i. Taking the complex conjugate of each side, that means the complex conjugate of the whole of the left-hand side must be the same as the complex conjugate of 0 plus 0i. Complex conjugate of 0 plus 0i is 0 minus 0i, which is still just 0. Now, just having a think again about our rules of conjugates. Rule 2 told me that if I had the complex conjugate of a sum, so if I had the complex conjugate of z plus w, that's the same thing as the complex conjugate of z plus the complex conjugate of w. And we commented that we could extend that to much longer sums. So, making use of rule 2, we can say we've got the complex conjugate of an times z to the n plus the complex conjugate of an minus 1 z to the n minus 1 plus all the way down to the complex conjugate of a1 times z plus the complex conjugate of a0 must equal 0. Now, rule 3, though, told me that if I have the complex conjugate of z times w, that's the same thing as the complex conjugate of z times the complex conjugate of w. So applying that to each of the terms on the left-hand side, we've got the complex conjugate of an times the complex conjugate of z to the n plus the complex conjugate of an minus 1 times the complex conjugate of z to the n minus 1 all the way down to complex conjugate of a1 times the complex conjugate of z plus the complex conjugate of a0 must equal 0. Now, the really important observation at this stage is that the polynomial p of x has real coefficients. In other words, the complex number an is just an plus naught I. It has no imaginary part. So the complex conjugate of an is the complex conjugate of an plus naught I, which is just an. So for all of those coefficients, an minus 1, all the way down to a1 and a0, their complex conjugate is exactly the original coefficient, because the coefficients are all real numbers. So we've now got an times by the complex conjugate of z to the n plus an minus 1 times the complex conjugate of z to the n minus 1 plus all the way down to a1 times the complex conjugate of z plus a0 must equal 0. Now using rule 4, the complex conjugate of z to the k is the same thing as complex conjugate of z raised to the power k. So rule 4 enables us to rewrite our equation as an times the complex conjugate of z to the power n plus an minus 1 times by the complex conjugate of z raised to the power n minus 1 all the way along to a1 times the complex conjugate of z plus a0 equals 0. In other words, z bar is itself a root of the equation p of x equals 0, because we've got p of the complex conjugate of z is equal to 0. So we've managed to prove the result that we're looking for. So, another example. We're told that minus 3 minus I is a root of the equation z to the 4 plus 4z cubed plus 3z squared plus 10z plus 50 equals 0. And we're asked to find all the other roots. Well, what we've got here is we have a polynomial equation with real coefficients. And if we have a polynomial equation with real coefficients, we know the complex roots must appear in complex conjugate pairs. So the fact that minus 3 minus I is a root means that the complex conjugate, that is minus 3 plus I, must also be a root. So we've got two of the roots now. Now the fact that I know that minus 3 minus I is a root tells me that z minus minus 3 minus I must be a factor of the polynomial. Similarly, the fact that minus 3 plus I is a root tells me that z minus minus 3 plus I must also be a factor of the polynomial. So putting those two factors together and simplifying the inner brackets there, well, z minus minus 3 minus I just becomes z plus 3 plus I, and z minus minus 3 plus I becomes z plus 3 take away I. So we've got z plus 3 plus I times by z plus 3 minus I must be a factor of the polynomial that we've got, z to the 4 plus 4z cubed plus 3z squared plus 10z plus 50. Now if we look carefully at z plus 3 plus I times by z plus 3 minus I, we've actually got a difference of two squares type format. We've got a plus I times a minus I, where a is z plus 3. Now we know that a plus x times a minus x is a squared minus x squared. z plus 3 plus I times z plus 3 minus I must be z plus 3 squared minus I squared. And z plus 3 squared minus I squared is z squared plus 6z plus 9 minus I squared, which is minus 1. So what we've got there altogether is z squared plus 6z plus 9, and then we've got minus minus 1 gives me plus 1. In other words, we've got z squared plus 6z plus 10. So z squared plus 6z plus 10 must be a factor of z to the 4 plus 4z cubed plus 3z squared plus 10z plus 50. So let's see whether we finish the factorisation off. So we're going to say z to the 4 plus 4z cubed plus 3z squared plus 10z plus 50 equals z squared plus 6z plus 10 times something. Now again, we can get part of the something really easily. We know that when we multiply the brackets out, the highest term we've got is z to the 4, so we must have a z squared starting off our unknown bracket. Similarly, the number term at the end of the expansion is 50. That must come from 10 times the number term at the end of our unknown bracket, so we must have plus 5 at the end of our unknown bracket. Now, as in the previous example right at the beginning of the video, we don't know what goes in the middle, so again we'll put in plus a times z. And what we'll do at this stage is we will again have a look at the z cubed term. So that's the second term along in the expansion. We know that we want 4z cubed on the left hand side, and then on the right hand side the z cubes are going to come from z squared times by az. That gives me az cubed, but I'm also going to get z cubes from the 6z times the z squared, and that's going to give me 6z cubed. So what I want is 4 to be the same as a plus 6, so a must be minus 2. Now at this stage it is well worth just stopping and checking that that works for the other terms. We know it works for the z to the 4 term, we know it works for the 4z cubed term. If we look at the z squared term, the z squareds, when we multiply out, we're going to have z squared times 5 gives me 5z squared. 6z times minus 2z gives me minus 12z squared. And then we've got 10 times z squared gives me 10z squared. So altogether then I've got 5z squared, take away 12z squared, plus 10z squared. And that, at the end of the day, gives me 3z squared. If you look at the z terms are going to come, when I multiply the brackets on the right hand side out, from 6z times 5, which gives me 30z, together with 10 times minus 2z, which gives me minus 20z. So I've got 30z, take away 20z, which is 10z, which again is exactly what I wanted. So at least now I know I have got a correct factorisation. So I've checked the other two terms work properly. Haven't quite finished yet, but I'm very close to having finished. I know that's my factorisation. I want to solve the equation z to the 4 plus 4z cubed plus 3z squared plus 10z plus 50 equals 0. So either z squared plus 6z plus 10 equals 0, or z squared minus 2z plus 5 equals 0. The z squared plus 6z plus 10 equals 0 came exactly from the fact that I knew that minus 3 minus I and minus 3 plus I were roots. So all I've got to do is solve the quadratic equation z squared minus 2z plus 5 equals 0. Again, we can use any of our possible quadratic equation methods for this, and we will obtain z equals 1 plus 2i or z equals 1 minus 2i. Now on our final page there's 3 examples for you to have a go at and see whether you can make some progress on those 3 examples. So question 1 is a couple of cubic equations, question 2 you've got a couple of quartic equations, and question 3, if you're really brave, we've got a equation of degree 5 to work with. So if you've got time, have a go at least 1 or 2 of these questions.